Good morning, everyone. Welcome back to the auditorium, our favorite auditorium for seminars. Thanks for coming. I will open with this because last week we didn't have great attendance. I learned that people were at conferences. Nice to see a lot of faces today here again. So today we have Daniel Pauli. He comes originally from Germany. I think he did his bachelor master studies in Bonn, then moved to Potsdam for his PhD, and now we have the pleasure having him here in Leuven as a postdoc in UX team, I believe. And definitely he already wins the record for the longest title. You have noticed that already. But titles do not really matter. What matters is what he is going to talk about. We are here to listen to him and not to read. Connie disagrees, but I mean, that's fine. That's usually my task to make Connie disagree on something. But back to Daniel, he's going to speak about massive stars, binarity, and at low-metallicity regime in the SMC. So, Daniel, the floor is yours.
Thank you. Yeah. So, long title, a lot of words. So, let's start with the first word. The first word is massive star. Yeah, I know we have the massive star mafia here, so many people of us are working on the massive stars, but there are a few that don't. So I decided to put anyways a slide here, and for the other, it's a nice reminder. So what is a massive star? It has an initial mass above 8 solar masses. These stars are super bright and therefore easy to detect and to analyze. So they have like luminosities about 3,000 times our sun, can go up to 1 million times. Some have even like 1 billion times the luminosity of sun. So they are really bright. And they have short lifetimes on the order of a few million years. And they have strong UV radiation-driven matter outflows, via which they lose several solar masses over the course of their lifetime. In most extreme cases, they can lose like half of their initial mass or even more. And the most important point is, most of the massive stars are formed in binary systems where they can interact with each other, which makes our life really bad, yeah. So because we have to consider also now binary stars and interactions, mass exchange, and so on. So what is the classical picture of like massive star evolution? So massive stars are born also when the giant molecular cloud collapses. We form like massive stars, normal stars. Massive stars are very rare, but they are super important because they are like very hot. They are temperatures above 15,000 Kelvin. They emit copious amounts of hydrogen ionizing radiation, and they stay at this hot stage like for at least 90% of their lifetime, sometimes even more. And given their short lifetime, they influence their surrounding like on an astronomical short time scale. And if you consider it on the galaxy evolution, it is like on the dynamical evolution of a galaxy. So if a star evolves, it will start to puff up, become a red supergiant. And if the winds are strong enough, it can shed off the hydrogen-rich envelope, and we can create like helium stars or Fourier stars. So Fourier stars are helium stars with strong winds. And these helium stars are even hotter than the OB star phase, and they emit helium and hydrogen ionizing radiation, so making them very important for like the reionization of the early universe that we see today. Right, and because they have so strong winds, they also deposit like lots of mechanical energy into their surrounding. They also enrich it with like heavy elements, and when the massive stars die, they explode a supernova explosion, leaving behind neutron stars and black holes. So, and the supernova explosion enriches the material even with heavy elements that we can find now on Earth, and also deposit like copious amounts of mechanical energy. So in galaxies, they are like the regulators of star formation. And the compact objects they produce when we have like stars and binaries, they are the progenitors of gravitational wave mergers. So you can see like massive stars are super important. But where does binarity come in now? So in the standard picture, what you assume is that if you have like a binary system, the star starts to expand, and at some point like the material gets like transferred to the other star, which leads to an official removal of the hydrogen-rich envelope. So binaries like produce tons of helium and Fourier stars that we should find in principle. So all of this makes massive stars like the main feedback agents in galaxies. Talking about galaxies, let's go to the third word, yeah, in the title. So high-redshift galaxies. So redshift is like this measure for distance and time. So if we look back in time, and the average condition in this galaxies is like different to our own galaxy. And the issue is that these galaxies are so far away that even with like modern telescopes, we cannot resolve like individual stars. So what we get is like the redshifted integrated spectrum. So it's like the UV spectrum and the optical spectrum that we can observe from these galaxies. And this spectrum is dominated by the most massive and most luminous stars. And so I'm showing here a spectrum of a high redshift galaxy at redshift 3.0. And you can see like P Cygni lines, which we associate like with winds from massive stars. So if we can model these, we can get information about the underlying stellar population. However, the average metallicity in these galaxies is lower. And why we think we understand massive star evolution at solar metallicity fairly well, we think. The properties of low mass stars is even worse understood, and the evolution of them. So, but there's hope, yeah? So we have the irregular dwarf galaxy, the Small Magellanic Cloud. It is nearby. It is a distance of 61 kiloparsecs, which means that we can resolve individual massive stars in this galaxies. In this galaxy, it has a low metallicity of 1/7 solar metallicity, which corresponds roughly to the average metallicity of galaxies at redshifts 2 to 5. And it has like tons of stars, so more than 1,000 massive stars, which means that we can also see like binary stars pre and post interaction. And so all of this makes the SMC like an ideal environment to study like the physics of low metallicity massive stars and binaries. The key questions I want to answer on this talk are about binary evolution. So how do binaries evolve in low metallicity? So from the galaxy, we know that the binary stripping is very efficient and can remove like the anti-hydrogen-rich envelope. But is this true also for lower metallicities? Then also, what about the stellar wind properties of these stars? So if I strip off like the envelope of my star, the stellar wind should be different, but we don't know what is the stellar wind of a partially stripped star and how it should look like. And in the end, I want to like combine the knowledge we gained about like binary evolution and stellar winds at low metallicity and understand what are the implications of the newly gained knowledge on our interpretation of integrated spectra of high redshift galaxies. Okay, tough task. What did I do? I searched for massive binaries in the SMC, obviously. And to do this, I obtained like multi-epoch optical spectra with the ESO VLT from my own program and also from the archives. And I searched for binaries more massive than 20 solar masses. And I also, so if I found a binary then, I asked for HST time to observe this star in the UV because I need UV spectra to obtain also the stellar wind properties. Okay, now I have this tons of data, but I also need to analyze the data. And to do that, I did like a spectral analysis with the non-LTE stellar atmosphere code power. And I did a fully consistent multi-wavelength analysis. So I'm modeling the optical and UV spectrum at the same time so that I can get like the stellar and wind parameters reliably. But to understand like the current evolutionary point of a binary that I observed right now, I also need to know its orbital configuration. So I analyzed the radial velocities I can get from my multi-epoch optical spectra, in addition to light curves whenever they were available to obtain like information about the orbital configuration and therefore also like about period and the orbital masses. Now I have my orbital and stellar parameters of my stars. And then in the last step, I wanted to calculate stellar evolution models to understand if current stellar evolution models can really like explain the observed properties of this post-interaction binaries that we see right now, or if there are issues. So in this talk, I'm going to talk about this 5 papers where we've discovered like 5 different post-interaction binaries. I will not go through each individual analysis in detail. I will use this star AZV476 as an example, and then I will put like the results of the other ones in the globular picture. So why did I choose AZV476 for this talk as my standard star, so to say? Yeah, so it is an early O-type eclipsing binary, so which means I can get an accurate period of this system and the inclination. And if I do then a consistent fit with the radial velocities, I also can get reliable masses because spectroscopic masses have large uncertainties, so orbital masses are the preferred way to understand the properties of the stars. Also, so you can see over here, there's an optical spectrum, and you can see the arrow is pointing towards the target that is sitting in the center of this nice H2 region, meaning that it has like a strong hydrogen ionizing flux, meaning that there might be some shenanigans going on. The spectral types are like an O4 giant plus an O9.5 main sequence star. And if you now do like a linear mapping between spectral type and the expected mass, you would expect that the primary has a mass of 50 solar masses and the companion has a mass of 18 solar masses. Sounds okay so far? So let's talk about binary evolution. As I said, I need information about the orbit to understand the evolutionary point of my system. So what I did is I modeled the light and radial velocity curve, which you can see on the left. And I obtained that the current orbital period is about 10 days of the system. That in the I-band, so the light curve was measured in the I-band, that the flux in the I-band, the flux ratio is about 30%, meaning that they have different luminosities, these two stars. And from the radial velocity fit, I obtained the orbital masses, and surprisingly, they had both 20 solar masses. So from the spectral type, we expected 50, and now we have 20. So there's clearly something going on. So if I have two stars with equal mass, what I also expect is that they have similar luminosity and similar temperature. But what I can see already from the light ratio is that they don't have similar luminosity, which means that there's some indication already that there has been some mass transfer maybe. Okay, but the spectral analysis will yield more information about this. So what I have done is like I calculated my power models, and to get the luminosities of the system, what you do is like you do an SED fit, which you can see up here. So in blue, I have like the observed flux calibrated spectra from different instruments, and the squares are like the photometric marks. The green and the blue dotted lines are like the secondary and primary synthetic spectrum, and the combination of the two, which should be compared then to the observations, is the red line. And in this model fitting routine, I also incorporated the knowledge that the flux ratio in the I-band should be like 30%. So what I obtained is that the luminosity of my primary should be like 5.65, which is about 1 order of magnitude brighter than the luminosity of the companion star, which is like consistent with the orbital analysis. And to at least put this star now in the Hertzsprung-Russell diagram and to understand its evolutionary standing point, we also need like the temperature. And the temperature is obtained by using like different ionization stages of the same element. For O stars, the prominent element would be helium. So you can see like a helium-2 line over here, a helium-1 line over here. I used more lines, but just for this presentation, I picked like 2 exemplary lines in a spectrum with like high radial velocity shifts. So you can see like this is a normalized spectrum in blue, and you can see like a narrow and a broad component contributing in both spectra. And from my stellar atmosphere analysis, I can now create like my synthetic spectrum. You can see in black and green again, like primary and secondary spectrum. In this case, unweighted, otherwise you would not see the secondary at least. And the red one is like the correctly weighted synthetic spectrum, which is compared to observations. And from this analysis, and also using other elements, I obtained like temperatures of 42,000 Kelvin and 32,000 Kelvin. Okay. Now we have temperatures, we have luminosities, we have the orbital configuration. Now we can put our star in a Hertzsprung-Russell diagram. And so here's a Hertzsprung-Russell diagram of the SMC. We have here the Wolf-Rayet stars, OB-type stars, the cool supergiants. And this is the position of the primary of the system. And as a reminder, so the orbital mass was 20 solar mass, and the orbital period is 10 days. So let's start with the unlikely case. The 2 stars have not interacted yet, so I calculated a single star model with initial mass 45 solar masses. And you can see, okay, it goes through the position in the Hertzsprung-Russell diagram where I would expect my star to be. And but the evolutionary mass would be like 43 solar masses, and is a factor of 2 too high compared to the orbital mass we obtained from the analysis. Okay, this might not be surprising because I said there might have been like mass transfer. So let's calculate the binary evolution model. So we can calculate the binary evolution model, and you can see like from the track, ghosts. So we can calculate the binary evolution model. At some point, my star has expanded enough, it will initiate mass transfer, and then it will contract towards the Wolf-Rayet stars. And this is roughly in the regime where we would expect to see, or where we observe our primary star. We can explain the current orbital mass and the current orbital period of the system. But, so I plotted these tracks with little dots, and each dot is a time step of 30,000 years. So if you see a lot of dots, it means it's very likely to observe my star in this phase. So you can see it should be like spend most of the time on the main sequence, most of the time as a Wolf-Rayet star. And if you look now in this contraction phase, this is a very rapid phase, so it is super unlikely to observe my star in this configuration. Okay, maybe we were just lucky, found like another of these impossible systems that we can observe and find too often. Let's compare this to the analysis of the other partially stripped stars reported in the other papers. So I extended now the Hertzsprung-Russell diagram to lower luminosities, and here are the positions of the other donor stars in this partially stripped systems or post-interaction systems. And you can see they all lie on the main sequence and hide among the OB star population, which is really surprising. Okay, if I now put their stellar evolution or stellar evolution tracks that are consistent with the orbital parameters of these two stars, you can see, okay, in this case, we also have like a short transition phase. So how can we have like 4 stars in a super short transition phase? So one can do now some calculations and see how many stars would I suspect to see like in different chunks of the Hertzsprung-Russell diagram. And you would expect like to see like thousands of helium stars. Bethany, who's new in our group, she has been working on this, and they have found the first few ones. It's not clear if we will see as many as we predict. This is like an open question for the future, but we would only expect to find like 10 stars in this partially stripped phase. And we already have found 4. And one has to say that the 3 lower mass ones were detected from surveys which were targeted to single stars. So it's not looking good for our statistics, to be honest. Another argument which is speaking against the current generation of stellar evolution models are the surface hydrogen abundances. So you can see they're color-coded like the star symbols of the donor stars in different colors, and they correspond to their surface hydrogen abundance. So if you have like a magenta star, it has like a high surface hydrogen abundance around 0.6, and if you have a pink one, it has a lower surface hydrogen abundance around 0.3, 0.4. I also plotted now my stellar evolution tracks in the same colors and overplotted them. And what you can see is that always after the mass transfer phase, they have a low surface hydrogen abundance, which doesn't agree with our observations. So there's clearly something wrong with the stellar evolution models. There are plenty of answers how to fix this. Yeah, for example, mass transfer efficiency, mixing, and so on. One solution could be that we are underestimating mixing efficiencies. So semi-convective mixing is a very poorly understood process, or at least the efficiency of it is poorly understood, let me say it like this. And semi-convective mixing is mostly important after core hydrogen burning, and what it does, it changes the structure of my star and reduces the maximum expansion. So you have in effect like more compact. You have more compact stars if you have a higher semi-convection mixing efficiency. So if I have a more compact star, this means if I initiate mass transfer, I'm losing I'm losing mass as long as my star is expanding. So if I have stars which are like expanding less, then I lose less mass during the mass transfer phase, which also means then that I lose less of my envelope. Then I have lowered surface temperatures, I have less helium-2 ionizing flux, and I have higher surface hydrogen abundances. So you can see in this massive star case where semi-convection becomes super important and has a strong impact on the evolution of the star, it actually never becomes a Wolf-Rayet star. And it's suddenly super likely to find my star here. So if I overplot again my stellar evolution tracks with the surface hydrogen abundances, you can suddenly see that we can see some sequence, so that we have like at lower masses still this efficiently stripped stars because semi-convection is not so efficient there yet. And if we go to higher masses, semi-convection becomes more important and impacts the structure of the star and therefore leads to higher surface hydrogen abundances. It could be that this is just like one solution that introduces more problems, so it needs like a more in-depth study, but it could be one solution. Other alternatives are like mass transfer efficiency, other mixing processes, missing physics, and so on. So one should not over-interpret this, but it is a nice solution which at least helps also like to explain at least the surface hydrogen abundances of our stars. For an evolutionary point, this also means that the final fate of my star can change. So if I'm talking about this massive star, yeah, it has like a high surface hydrogen abundance, will never lose its hydrogen-rich envelope, and therefore it will explode as type 2 supernova and not as type 1 BC. So this could have like a huge impact on how we understand like the dynamics in the stellar population. Okay, now that we have finished like binary evolution, let's talk about stellar winds. So to determine the mass loss, so stellar winds are quantified by the mass loss rate, yeah, and you can measure it from P Cygni profiles in the UV spectrum of a star. So I put like red boxes where you can see like typical lines used to determine the mass loss rates of my stars. So, and if I now calculate my stellar atmosphere models consistently with the optical spectra, of course, then you can see that the primary star, the black dotted line, is dominating the UV wind features. And it is really leading to strong P Cygni profiles, while the secondary is just like having no wind. This is consistent for an 09.5 star. At SMC metallicity, you don't expect them to show any wind signatures anymore. And it's actually leading like to this filling of this absorption trough due to its like UV flux contribution. So what I determined is that the mass loss rate of my primary is like 10 to the power of -6, which means every 100,000 years it loses 1 solar mass, which could lead to an efficient stripping, and it will lose like several solar masses before it will explode in the end. Okay, so -6.1 sounds is a nice number. So how does it compare to like other stars? So in the upper part is again the spectrum of the binary that I just presented, and in the lower one I'm showing the spectrum of NGC 346 SSN 13. This is an O star which has the same luminosity and the same temperature as the donor of our system. And you can see in the UV that the wind lines are actually way weaker, and this is because its mass loss rate is like a factor of 10 lower than compared to our donor stars. So something after the stripping has to lead to the fact that I have like an enhanced mass loss rate, and also therefore like stronger UV features compared to like a normal O star with similar properties. So again, this is only one data point. I can do anything with one data point. So let's see how it looks in comparison to the other partially stripped stars. So what you can typically see in papers is that you see like the mass loss rate as a function of luminosity. And I plotted here some data points of main sequence stars in the SMC. You can fit a line through it if you want to guide your eye. You can do the same for the Wolf-Rayet stars. You can already see the Wolf-Rayet stars have like a factor of 10 higher mass loss rate than the O-type stars, which seems to be interesting because it's like a similar shift like the partially stripped stars do have. And if I now add my partially stripped stars, you can see again that for all of them I can see at least like a factor of 10, even 100 sometimes increase in mass loss rate compared to an O star with the same luminosity. Now your eye might trick you and you say, okay, so they are in this evolutionary phase between the main sequence and this Wolf-Rayet or helium stars, so you just can like extrapolate this fit and tada, they all lie on the same line. Yeah, but unfortunately the picture gets worse, so I can now include like supergiants and suddenly like everything in between is filled. So the wind strength of this partially stripped stars is like comparable, maybe something like supergiants or Wolf-Rayet stars, but how do they really align? So, and the answer is I'm tricking you. So because luminosity alone is not the only factor responsible for driving the stellar wind. What is actually responsible is like the radiative acceleration and the gravitational deceleration. So you have like the wind pushing material away and the gravity like trying to keep it on the star. So in principle, on like as a first order approach, you can say that the mass loss rate depends on the acceleration and deceleration, and which is in principle just the adding factor. And it depends on the luminosity, so how much radiation do I have to power, the mass, which is like pulling it back, and the opacity, which means how well my radiation field couples with the material. Unfortunately, if I analyze the star, I don't know the full opacity, yeah, because this is like the mean opacity at a specific optical depth. So what is typically done is that I use just like the electron scattering as a zeroth order approach. So then my mass loss rate is just a function of the classical Eddington factor. And here I'm showing like a plot where I have like mass loss rate as a function of the classical adding factor. And you can suddenly see that all my stars align on a straight line, at least on first order. There's some intrinsic scatter, which comes from wind variability, different analysis methods, and so on. But they all lie around the same line. And the explanation why we have like the strong enhanced wind of the partially stripped stars is just because they are like close to the Eddington limit and therefore have like the ability to power a strong stellar wind. Okay, puzzle solved. This is, by the way, a paper I just submitted this week, so woo. Thanks. Okay, last point, the spectra of high-redshift galaxies. So before I talk about like thought experiments about the implications for high-redshift galaxies, let's use like a young cluster, because a young cluster has the opportunity that it has a constant age. I know the stellar content, so this is the cluster NGC 346. It is in the SMC. It has like 20 O-type stars, and I can see like which star is contributing how much to the integrated spectrum of this young cluster. So it is like ideal to understand like the impact of individual stars in the integrated spectrum of a distant galaxy. And I'm also only interested in like the OB and Wolf-Rayet stars, because what I can see of the redshifted galaxy is the UV and the optical parts, so red supergiants do not contribute to the spectral range. Okay, so Matthew Rickard and I, we have done an analysis of these O-type stars in this cluster. And so here are the UV spectra. They are sorted like from brightest to faintest star. And you can see like many main sequence stars, they actually do not show like these carbon-4 p Cygni profiles. Only at the like very luminous, also the very massive end, you can see like p Cygni profiles popping up. Also for nitrogen 5. And you can see that the brightest star, it's actually a binary, so it's an interacting binary that we have analyzed. And and this is the star with like the strongest wind feature. Then there's like SSN9, which is also a binary. Shit. So the two stars, which are like the brightest stars and showing the strongest p Cygni lines or the strongest UV wind features, are both binary stars and potentially both already partially stripped. So at low metallicity, this means that partially stripped stars actually might matter. So let's make like a little thought experiment. Let's assume we have like a starburst galaxy where we had a high star formation rate. We have a lot of stars there, and all stars have the same age. So if we are at a young age, like in the cluster NGC 346, then you will see that the UV flux is coming, and the UV wind features are coming mostly from the most massive O-type stars and also from the post-interaction binary, so especially like the donor stars there, because they are closer to the Eddington limit. If we let time progress, most massive stars will die. And what happens is that the most luminous stars will become the partially stripped stars, because as we have seen in the stellar evolution calculations, after the stripping, my star is more luminous than before. So if all the other stars have died, the most luminous stars are the partially stripped stars, maybe helium stars, and maybe a few supergiants. And all of them are then the sources which are like contributing to the UV wind features. There will be also like UV flux contributions from the other stars, but for the wind features that we can see in the integrated spectrum, it's mostly the partially stripped stars. So last thought experiment, so if we talk about constant star formation, then we have continuous star formation and a continuous production of Wolf-Rayet stars and helium stars, as we can see in the SMC. And they will settle to an equilibrium state according to the lifespan of the different evolutionary phases. So if you have 100 O stars, you will see 10 Wolf-Rayet stars. And the brightest stars are the Wolf-Rayets and maybe a partially stripped star. So these are the ones dominating then the spectrum of an of the stellar population. Okay, time for a summary. I'm quick. I reduced and analyzed new HST UV data, multi-epoch ESO data of the most massive stars in the SMC, and I discovered and analyzed 5 post-interaction binaries using the power code and the orbital analysis done with Phoebe, and then I compared it to MESA. And what I concluded from my analysis that most massive post-interaction binaries have enhanced stellar wings due to their proximity to the Eddington limits. So now we have finally a way how to do this, because in stellar evolution calculations, it's typically just a phase where you just roughly interpolate through. But if it is long-lived phase, this interpolation can come with like some dangers. What we have learned from the partially stripped stars that we have discovered, that there are too many and that they have too high surface hydrogen abundances, which is challenging our current stellar evolution models, and that we might have there some missing or misunderstood physics in our models, which then also has like strong implications for the final fates of my massive stars, and also like for the ionizing fluxes and the feedback within an entire galaxy. Thanks.
Thanks, Daniel, for an interesting talk. We have plenty of time for discussion.
Thanks, Daniel, for the great talk. I actually have a question about the first part of your talk. What was the value of semi-convective mixing that you assumed in your models?
Oh.
Do you remember?
Yeah. So in these models,
yes.
Yeah, which are doing wrong, which are underperforming, I used a semi-convection efficiency of 1, which was calibrated by Abel Schotemeyer using single stars and yellow and red supergiants. But they could not tell like if it should be something like 1, 10, or 100. So in these models, I'm using 10. Okay. There's also work from Jakob Klenke, if you're interested in this, who uses even more efficient semi-convection of 33. And in his case, like if a star initiates mass transfer, it just stays at the position where it has like initiated mass transfer. So 33 might be too high. So if you want to use semi-convection to compensate for this observational difference.
Another related question. Okay. So just trying to understand the thought process, because there are many things that can change the expansion of star. I mean, radius is in general very sensitive to input parameters. Why semi-convective mixing? Like you could have gone to other things. I'm trying to think. But yeah, what did you test other factors as well, or?
No.
It was just like, okay, let's try this.
So I tested semi-convection because I was aware of these papers I just mentioned from the other people, and it looked like a good explanation.
Yes.
I did not test other things. This is why I said like maybe I'm just like overfitting at some point, and maybe it is some different physical process which is leading to the same stuff. But given the time frame of 4 years for a PhD, I couldn't test more stuff.
No, this is great, and I think this is very important, because often the role of semi-convective mixing, based on like old papers, is only considered for like blue loops and stuff. So only in that, that's where it mostly shows differences. But it's amazing to see that even here for partially stripped stars, it's quite. I mean, this is the first time I've seen like second case where semi-convective mixing is important. Thank you.
You're welcome.
Thank you. Very nice talk. I have a question about this last point here, that they will explode more as a type 2 than type 1b/c supernovae. We already have an issue where we're not seeing red supergiant progenitors of higher mass type 2 progenitors. Where are the type 1b/cs coming from if we have this reduced envelope loss?
Excellent question. So what I'm showing here is case B mass transfer. Yeah, so in case B mass transfer, you have time for semi-convection to work and to impact your stellar structure. And in this case, it could be that if you have case A mass transfer, so you have case A and then case AB mass transfer, which is more efficient in stripping of more of the hydrogen-rich envelope, and therefore you could still like explain like Wolf-Rayet stars and partially stripped stars, or fully stripped stars, sorry, that we observe. And this could be like progenitors of one type BC supernovas, and so all of these systems are case B systems, yeah, because of their period estimates. And but it could be that case A also leads to these stars, common envelope evolution. So there are other channels which could lead to like fully stripped stars, and also like to this partially stripped stars.
Cool, thank you.
Thank you for your great talk, actually. The most problematic aspect of your whole talk are the models. And so going back to the semi-convective mixing, that's a phenomenon, if it occurs, that should also work in the single stars. So what I would like to see is, and maybe it's more a question for Bethany, actually, in your sample of, hi, welcome. In your sample of, I mean, what makes your star different from single stars are tidal forces. And I suspect you have a good handle on surface rotation as well. So have you a table of the force balance in terms of gravity, radiation-driven force, the centrifugal force, the Coriolis force, and the tidal force? That's what I would like to see compared, because tidal effects give waves and they mix, and that's not in MESA. Just
then it's not
comment.
my models.
So I mean, I understand your reasoning that you looked at one type of mixing. I'm just saying that maybe you should look at mixing phenomena that are different for single versus binary stars. That would be interesting. I don't know if such a table exists, but maybe she can have.
Some of the systems seemed like they were at longer periods, or for me, like 10 days. Do you think those tidal forces would still be relevant even at larger separations, as opposed to like, usually tidal seems to me to be more relevant at like hours or like a couple days or something? Yeah. Okay. I have one other question too about the winds. So it's really interesting that the partially stripped stars have similar winds to the Wolf-Rayet stars. The more fully stripped stars that I'm finding are deficient. Like they have like maybe order of magnitude less or so. Yeah, like you show here. Is that just a consequence of like the luminosity drop off, that you lose a lot of the envelope, you don't have like the sub-Eddington, or are there any other effects that contribute to that?
So I looked at the upper limits given in the paper you're referring to about this fully stripped stars, and they would be here. So the Eddington factor drops because if you stop burning hydrogen in your shell, then your luminosity drops and you go to lower Eddington factors, and also because your surface hydrogen disappears. Yeah, then you are positioned somewhere over here, and the stripped stars you find have low mass loss rates of -8, -9, and they are in this region of the diagram.
That's an upper limit, and it's like around -9, and like it could be lower.
Yeah. I mean, it's also with spectroscopic masses, so the uncertainty is something like this.
Oh, there are also evolutionary model masses too. There's both.
Yeah.
From the mass luminosity relation.
I'm not sure if I want to trust evolutionary masses, to be honest.
Okay.
But yeah, so far there is no discrepancy. Yeah. If you get the accurate wind lines, I mean, the issue is that these partially stripped stars you find, they also don't show like features in the UV, because I mean, we can see this also. It's called the wind weak problem. It's the question if the wind is then like in the X-rays hidden. And so far we cannot observe an X-ray spectrum at SMC metallicity easily for the stars. And in the optical you also don't see like wind lines from the stars. So therefore the upper limit is like what we have right now. Yeah. But if you give new numbers, maybe we can see that there's like a turn-off. So in the galaxy there would be some stars over here which are like this weak wind problems, and they just lead to a cutoff. So. And I know for the Wolf-Rayet stars from theoretical model efforts of hydrodynamic models that you also expect at some point that their mass loss rates like drop off, and because they transition then to optically thin winds, and that their wind signatures change. And maybe this is the same also for the OB type stars or the helium stars with optically thin winds. But this is speculation.
Very cool.
Yeah.
Thank you for the great talk.
Thanks.
We still have time. Oh, Alex.
Yeah, hi, and great talk. I just wanted to ask about the accretors. So the secondaries for these systems, are they suitable for exploitation, and do you have plans to incorporate them into your modeling? Because one thing that you potentially have here, model dependent, sure, but you could place constraints on the post-interaction timescales. And then from that potentially makes this quite a very interesting and even useful sample for for studying the accretors as well, because you would have an actual constraint on how long it was since they accreted, quite precisely because the evolution is so rapid in that area, in fact. Is there like plans to exploit this, or are they not suitable?
So the stellar evolution calculations I did are all with a secondary companion, and the mass accretion is limited by rotation. I didn't do a comparison yet. So for this star, we have a rapidly rotating star. I did in this paper a comparison, and I didn't find many differences. I mean, the rotation was a bit lower, but this is a known issue that if you have like Wolf-Rayet stars with O-star companions, that the O-star companions are rotating like at 80% critical rotation, while the MESA models would say like, it should be like at critical rotation because the time scale is not long enough to spin down my star. So I have the same issue here for the secondary. Yeah, but otherwise I didn't do a comparison yet, so could be an interesting project.
There's still time for questions. Don't be shy. It works, huh?
Thanks for the talk. If you could go to the spectra, some slides ahead.
The UV spectra or the optical?
Yeah, where you have like 2 stars on them. Just 1 or 2 slides ahead. Yeah, this one. I was wondering about the Lyman alpha. You haven't said anything about it because in the upper one you have Lyman alpha that goes through the roof. In the lower one there's just a tiny emission. I don't know what's up with the Lyman alpha here. So maybe you can talk about it.
Lyman alpha is interstellar absorption, and it depends on the reddening. So this star is like enshrouded in this H2 region, which has like higher reddening, and this cluster, this NGC 346. Yeah, as you can see, we can look clearly in this. So the stars, the massive stars, are not like hidden behind something, so they have lower reddening values, and therefore the Lyman alpha absorption is a bit narrower than compared to the other one.
Well, that's in emission.
This little emission peak.
Yeah.
I'm not sure, it might be like nebula emission then, and you have this absorption coming from the interstellar absorption. And this the peak is, I think, from nebula lines, which is not subtracted from the spectrum because it is so strong. And I mean, here's also a little dip. They tried to remove it in this one, but in this one, this is like with an automated pipeline. This is from a manual like analysis where they extracted the spectrum of the star.
Okay, thank you.
This is COS, and this is this, but this is this slit, I think, and then extracted because there were multiple stars inside. So
in the COS data, it's an aperture, it's a circular aperture and not a slit, and everything is integrated. So you have the sky, the nebula, and the stellar spectrum. While at the bottom, because it's a slit, then you can do sky subtraction and nebula subtraction.
Good to know.
There is still time. Don't be shy.
You mentioned that this, you're assuming the electron scattering opacity. How much do you think that assumption is affecting your trend line? Do you think if you used a better one, it would widen it, make it broader, or would it be more?
It's a good question. So if you go closer to the Eddington limit, the differences get stronger, is the answer. So I might be doing like wrong up here, but anyways here the uncertainties are larger for this Wolf-Rayet binaries because the masses are also quite uncertain because of the emission lines. They're hard to determine. And so how much do I expect it to differ? I think if you go like as close as 50% to the Eddington limit, then you start to see like noticeable differences in the full Eddington factor and the electron scattering one. But I mean, it's still aligning with the line, and I don't have the information of the full opacity, so I cannot calculate this one. So the values I quoted, like when you see this difference, are from theoretical modeling efforts of Wolf-Rayet stars, which are close to this Eddington factor.
Thank you.
Still have time. While people are thinking, going back to slide 28 and comment that the biggest problem in your talk are models. Well, it's a nice way to explain the position of your star with MESA models. But maybe you mentioned that, I missed it. If that's the case, sorry. But how do you explain Wolf-Rayet stars then? Because your models do not go there anymore.
So it's a very good question because the Wolf-Rayet stars have many problems. So they have like 40% binary fraction. Is it true? 40%? I don't know, something like this, plus minus 10%. So, and the faintest one are also like the apparent single stars, and there have been like dedicated searches for this. So they are a problem by themselves. But in principle, with this model configuration, if you have binaries, these Wolf-Rayet stars could come from case A mass transfer, and therefore should be like located here because the case A is more efficient in stripping off the hydrogen-rich envelope, and case B is not. And from Huyg's work, we have learned that most massive stars formed in binaries have like prefer the shorter periods. It's true, yeah? Okay, good. And therefore, so it could be that they're coming from case A in this scenario. If you believe it is something different, so it could also be that because they are like the single stars, it could be that we are doing wrong with red supergiant winds, and if you have a stronger red supergiant wind, then you can also explain them as single stars.
And do the numbers add up in terms of, like, if you have these hundreds of single all-stars and a few of those binaries in this MESA scenario, do you really expect just a few Wolf-Rayet stars created through that channel, or you would expect less or more?
I have not done the population synthesis, but it would be worth looking at it. So I cannot tell you the numbers.
Alex? Yeah, but you can do it. But you can do it. So maybe that's something you guys can then discuss offline. And I also had a second question here. So you started to play with MESA models, kind of assuming, and you made that statement at some point, and Connie nicely repeated it afterwards, that we kind of have a problem here with the models. But I think there is one more thing you could play with in this diagram, and that's the position of the star itself. Taking a step back, do you really have that much trust in all the stellar atmosphere models, in your power code, in all the physics that is in there, that you kind of assume that, okay, that's my position of the star there, and not lower, to the left, to the right?
So the luminosity, I would say, is like pretty accurate known. I mean, the uncertainty is 0.1 dex, yeah, in luminosity. So it's not so much. They are not moving from here to here or something like this.
Statistical uncertainty or systematic uncertainty?
This is so because we know the distance to the SMC very well, yeah, and the individual distances in these galaxies do not matter so much. And it depends a bit on the reddening law that you are using. But if you play with different reddening laws or like with different temperatures which determine like the UV flux that you have and need adjustments, and the typical uncertainty you can see is on the order of the 0.1 dex. So for luminosity, I think we are quite certain that the luminosity is true. And for the temperature, of course, in this stellar atmosphere codes, we have like underlying model atoms, yeah, and if they are wrong, you have like a transition which would lead to too much pumping into a specific state, then you would be like overfitting a specific line. But to derive the temperature, I'm using like over 50 lines, which I can see in the entire spectrum. So either we are doing like super wrong with our stellar atmosphere models, or the luminosity is fairly good known, up to like a few thousand Kelvin. So there also has been a study from this XUDU collaboration where people have analyzed like 3 different stars, and everybody used like their own spectral analysis method. So like by eye, like systematic fitting, and the conclusion was that all of them agree within their uncertainties, and that the difference between the derived temperatures is about 10% at most. So they are moving a little bit in this log space, but not too much. And this codes have been developed independently of one another. So it's not like somebody has stolen something from another person, but they have like invented their own things, and therefore there are slight differences. But the systematics doesn't seem to be like too huge that we cannot trust like the spectral analysis.
And in that exercise, I understand that different codes have been used, but to me it only proves that those codes are bug-free. Otherwise, they use the same fundamental physics underlying, right? So if there is something fundamentally wrong, then they will all be wrong, right?
Yeah, if there's something fundamentally wrong, then we are doing wrong since 60 years. But I mean,
that would be sad.
That would be disappointing, yeah. But I mean, then not only the stellar evolution models are wrong.
I think we can look at it differently. I would think that we can trust the data measurements, the temperature and luminosity, way better than we can trust MESA.
It's nice to see that. It's nice to see that Uke is an optimist. It's very good for master students.
But he's running away from you. He made a statement.
He's afraid of me. You didn't know that? That's not the news, eh? We still have like a couple of minutes for a very last question until you guys are all hungry. Then 2 questions. Start with Shri and then.
Hi. My question is actually related to Reynold's last question, I think, when you talk about those opacities. I was wondering if that relation will also not be affected by metallicity?
It is. Actually, this is what my paper is about, so you cannot see it, but so in this equation, the full opacity encompasses also information about the metallicity itself. So if I fit this for the SMC metallicity is roughly constant. Yeah, there's no chemical gradient known. So for this plot, this is okay. But in the paper I submitted, I studied, made a big literature study, like using all data I could gather from all the spectral analysis of like stars in the galaxy, the LMC, the SMC. And of course, if I then would like only fit it in this relation, then I would be neglecting the fact that metallicity is changing. So I have to add another proportionality to metallicity then.
That's what I'm thinking.
Yeah.
Okay, just one small question. Do you, for the stars where you see the P Cygni profile, do you also, do you have multi-epoch observations for them, and do you see this everywhere, or?
What do you mean? Like
this one, as well as in the later slides, you show some stars with the
for
high
this star, I
luminosity.
actually have 2 UV spectra
And
at different orbital phases, and I can see that only like the P Cygni profile is moving, and there's no like step or something like this coming, so there's really no contribution of the secondary.
Okay.
For the other ones, I don't have it, so it could be, I mean, the stellar winds are not always stationary and they are somewhat variable, so it could be that we are just looking at a snapshot and maybe we are like overestimating, and this is why you can see this huge scatter around the data points, because I don't know if these winds which I'm considering here are like variable, so it could be that if I'm looking at a bad instant where it has like a boost in mass loss, then I'm measuring the mass loss rate wrong.
Yeah, okay, thank you.
My question was also about metallicity, but from the model's point of view. Because, of course, coming back to the semi-convective mixing and any other mixing phenomena, let's say, they depend largely on the chemical mixture that you assume for your star. So do you have LMC, SMC, one-on-one comparison of these type of stars? Again, I'm asking sort of for a table, like similar stars, but then at different Z value.
So this model I only calculated at SMC metallicity. I didn't do the exercise to do it at LMC metallicity. But about the chemical composition of my models, I made sure that the chemical composition is the same as I'm using in my stellar atmosphere models, so that I'm consistent in itself. That's everything I can answer to your question. I don't have a table, sorry.
We have a phase of increased activity here, but that's the last question.
I was really trying to not ask you this question because I feel it will be outlier, but given the last few questions have been around this topic. So you said that you made the chemical composition was same. What was it close to solar? Like what exactly did you use? The point I'm trying to bring up is about alpha abundances, because often we use certain metallicities, and which is great, like you use SMC, but the individual abundances are then close to solar or solar calibrated. And I was recently reading a paper for BPAS models, and they have calculated a grid of stellar models with different alpha abundances. And it's quite interesting to see that how, when you vary these alpha abundances, you're essentially varying like iron and other things as well. And you can get, like, for the same metallicity, alpha abundances can actually do like quite a lot of changes in stellar evolution, say.
So for iron, silicon, magnesium, carbon, oxygen, nitrogen, I'm using tailored abundances measured from different stars, regions, whatever in the SMC. So they are consistent with the SMC metallicity. For all the other elements which cannot be seen in any spectrum, I simply used a scaling factor of 1/7 for solar metallicity from Asplund.
And where your
other
solar
updates.
metallicity was?
The average metallicity in my models is something like 1/7 solar metallicity.
Okay.
Yeah.
So one of the newest compositions.
Yeah.
Okay.
All right, we are at the hour. Let's thank our speaker again. Thanks for coming. See you next week.